Our goal is to establish a general formula for the determinant. Such a formula involves permutations, which we are going to discuss next. So let's give a definition. A permutation of length n is an invertible function from a set of integers from 1 to n to the same set. Let us mention a piece of terminology. So instead of saying a function, we will sometimes use the word mapping or just the word map. So here, traditionally functions are used in analytic context, so when we want to discuss continuity. And mappings, so it's the same word for function, so it's a synonym, but it's more used in geometric context. And like northern people who have a multitude of words for various grades of snow, so mathematicians have more than one word for the notion of function. And so let us recall that so a function, so f from some set a to b, is invertible if and only if f is bijective. And the word bijective means that f is simultaneously surjective and injective. Let us give an example of a permutation. Let us take n to be 6, the length of a permutation. So here, so we take the domain, so 1, 2, 3, 4, 5, 6, and the target set, which is the same, 1, 2, 3, 4, 5, and 6. And now we construct a permutation. So where 1 goes to 4, 2 goes to 6, 3 goes to 1, 4 goes to 2, then 5 goes to 5, and 6 goes to 3. It is customary to use Greek letters to denote permutations. So if this permutation is sigma, then there is a more compact way of denoting it. So in the top row, we will write all first 6 integers, and then at the bottom row, we specify what are the images of these numbers. Say 1 here goes to 4, so we write a 4 here. So 2 goes to 6, 3 goes to 1, 4 goes to 2, 5 goes to 5, and 6 goes to 3. This is a compact notation that encodes this diagram. And the same permutation, when viewed as a function, is given by the following values. So we can write sigma of 1 is 4, sigma of 2 is 6, sigma of 3 is 1, sigma of 4 is 2, sigma of 5 is 5, and sigma of 6 is 3. So we see that we have several ways to describe a permutation. Now, let us list all permutations of length 2. So here we have the following permutation. So 1 goes to 1 and 2 goes to 2. And the second permutation is where 1 goes to 2 and 2 goes to 1. So we see that there are two permutations of length 2. If we take permutations of length 3, then we get more of them. So we could have 1 goes to 1, 2 goes to 2, 3 goes to 3. So then we could have 1 goes to 1, 2 goes to 3, 3 goes to 2. Then we could have, so 1 goes to 2, 2 goes to 1, 3 goes to 3. Then we have 1 goes to 2, 2 goes to 3, 3 goes to 1. So then we have 1 goes to 3, 2 goes to 1, 3 goes to 2. And finally, we have 1 goes to 3, 2 goes to 2, 3 goes to 1. So here we have 6 permutations of length 3. And the set of all permutations of length n is denoted as Sn. So Sn stands for the set of all permutations of length n. So here we have a list of elements in S3, and here we have a list of elements in S2. Let us state the following proposition. The number of permutations of length n is n factorial, so which is the product n times n minus 1 times n minus 2 times 2 times 1. To prove this proposition, let us think, how can we build a permutation? To build a permutation, we need to choose the value for sigma of 1. And how many options do we have for choosing sigma of 1? Well, sigma of 1 must be an element from the set from 1 to n. So this means that we have n options for choosing the value sigma of 1. Now, suppose we have chosen one value to assign to sigma of 1. Then how do we assign sigma of 2? We recall that a permutation must be injective. So this means that sigma of 2 cannot be equal to sigma of 1 because of injectivity. And because of this, so now we have only n minus 1 options for choosing the value of sigma of 2. And then when we choose sigma of 3, we are not allowed to use values sigma of 1 and sigma of 2. And then this leaves us with n minus 2 options. And so on. So when we come to sigma of n, then because all other values are already taken, so there will be only one possible value left. So for sigma of n, we have a single option. And so then, if we look at the total number of our options, then we obtain the product n times n minus 1 times n minus 2, and so on, all the way down to 1. And this number is called n factorial. Let us now discuss natural operations on the set of permutations of length n. And so the first operation is composition. And we recall that a composition of two invertible functions is invertible. So this is simply true because we have an explicit formula for the inverse of the composition. So if we have two invertible functions, then the inverse of their composition is G inverse composition with F inverse. And as a consequence of this, so we conclude that the composition of two permutations of length n is again a permutation. Let us look at the following example. So let us compute sigma composition with mu, where mu is the following permutation. So 1, 2, 3, 4, 5, 6. So 1 goes to 3, 2 goes to 6, 3 goes to 1, 4 goes to 2, 5 goes to 4, and 6 goes to 5. So when we write sigma composition with mu, so then in these notations we recall that our convention is that mu is applied first. So how can we calculate this composition? So diagrammatically, so what we do is we draw the diagram of mu and the diagram of sigma. So for mu, we have the following diagram. So 1 goes to 3, 2 will go to 6, then 3 will go to 1, 4 will go to 2, 5 goes to 4, and 6 goes to 5. And now, when we compute the composition sigma with mu, so we just trace the arrows. So here we see, well, mu is applied first. So under mu, 1 goes to 3, and under sigma, 3 goes to 1. So 1 goes to 1. Under mu, 2 goes to 6, and under sigma, 6 goes to 3. So in the composition, 2 goes to 3. So under mu, 3 goes to 1, and then 1 goes to 4. So 3 goes to 4. 4 goes to 2, and 2 goes to 6. 5 goes to 4, and 4 goes to 2. And 6 goes to 5, and then 5 goes to 5 by sigma. So we get 6 goes to 5. So the result is that the composition of sigma with mu is this permutation. And we keep in mind that mu here is applied first. We point out that in general, the composition of permutations is not commutative. So this means that sigma composition with mu should not be expected to be equal to the composition of mu with sigma. Let us do the calculations for this example. So here, if we now apply sigma first, so then we get the following diagram. So we have the arrows going, so from 1 we have the arrow that goes to 4, from 2 we have an arrow to 6, from 3 we have an arrow to 1, from 4 we have an arrow to 2, then from 5 we have an arrow to 5, and from 6 we have an arrow to 3. And now for permutation mu. So we have 1 goes to 3, then 2 goes to 6, 3 goes to 1, 4 goes to 2, 5 goes to 4, 6 goes to 5. So this diagram allows us to compute the composition of mu with sigma, so where sigma is applied first. So let us trace the arrows, and we see that 1 first goes to 4 and then to 2. 2 goes to 6 and then to 5. 3 goes to 1 and then to 3. 4 goes to 2 and then to 6. 5 goes to 5 and then to 4. And 6 goes to 3 and then to 1. And so when we compare sigma composition with mu and mu with composition with sigma, then we see that the results are completely different. The second natural operation on the set of permutations is taking the inverse. And by our definition, a permutation was an invertible map. So this means that the inverse by definition exists. And we calculate the inverse by reversing all the arrows. So if we want to calculate the inverse of this permutation mu, then we get the following permutation. So under mu, 1 goes to 3. So under mu inverse, 3 will go to 1. Then under mu, 2 goes to 6. So under the inverse, 6 will go to 2. Then 3 goes to 1. Under the inverse, 1 will go to 3. Then 4 goes to 2. Under the inverse, 2 will go to 4. So 5 goes to 4. Under the inverse, 4 will go to 5. And 6 goes to 5. Under the inverse, 5 will go to 6. So this is the inverse of the permutation mu that is given here. Let us state some properties for operations on permutations. So the first is the associative law for the composition of permutations. So if we have sigma composition with mu and tau, so this is the same as the composition of sigma with mu, composition with tau. So this is called associative law. And this law holds because it holds not only for permutations, but for compositions of arbitrary mapping. So this is a very general property of compositions. And in particular, it holds for permutations. So the second property is the existence of identity permutation. Let us define identity permutation, which is denoted by letter E. So this is a lazy permutation that sends 1 to 1, 2 to 2, 3 to 3, and so on, n to n. So for each length n, we have an identity permutation as an element of Sn. And the properties of the identity permutation is that, so if we first apply identity permutation and then take a composition with any permutation sigma, so because the action of identity has no effect, so the result will be equal to permutation sigma. And the same will be also true in the opposite order. So if we apply first sigma and then we do nothing, then the result is equal to sigma. And finally, so the property of the inverse permutation is that the composition of sigma with sigma inverse and the composition of sigma inverse with sigma is equal to identity permutation. So this is basically the definition of the inverse permutation. Next, let us introduce one of the important notions in mathematics. So definition. A group G is a set with a distinguished element E called identity, an operation of multiplication denoted x times y, and operation of taking an inverse denoted x inverse, satisfying the following axioms. So 1 is the associative law that says that for all x, y, and z in the group G, x times y times z is equal to x times y times z. Then 2 is the axiom of identity, which says that for all x in G, x times identity and identity times x is equal to x. And 3, the axiom of inverse that says that for all x in G, x times x inverse and x inverse times x is equal to identity. It turns out that these 3 simple axioms lead to a very rich and beautiful theory, and we will study group theory in more detail in the 2nd and 3rd year of algebra. And so here we will just give a very basic introduction into the definition of the group. Let us give a few examples of groups. Well, the first example is the one that we discussed today. So this is the group of permutations Sn. So what we saw is that on the set of permutations, so we have well, a distinguished identity element, which is the identity permutation. Then we have operation of composition of permutations, and in the context of group theory, this operation is called also multiplication. And we have the operation of taking the inverse permutation. And all 3 axioms of the group will hold. So we have the associative law for the composition, then we have the axiom of identity for the identity permutation, and the axiom of the inverse will also hold for the inverse permutations. So this tells us that Sn is a group, and the name for this group is called, so this is called symmetric group. And thus the notation Sn. So S stands for symmetric. The second example is let's take the set R star. So these are non-zero real numbers. And let's take the operation of multiplication, right? And we know that the product of 2 non-zero real numbers is a non-zero real number. So this means that this set is closed under operation of multiplication. And it has the identity element, which is the real number 1. And this identity will satisfy the axiom of identity. And also we have the inverse, right? So here x inverse is defined as 1 over x. And so with these operations, we see that the set of real non-zero real numbers becomes a group. Our third example will be the group which is called GLNR. So these are invertible n by n matrices. And so the name for this group is, so this is called general linear group. And indeed, so we have the identity element in this group is the identity matrix. And the multiplication operation in this group is multiplication of matrices. And we know that the product of two invertible matrices is invertible because we have an explicit formula for the inverse of the product of two invertible matrices. And we see that multiplication of matrices does satisfy the associative law. So we have the axiom of identity and the axiom of the inverse. So this tells us that here we have yet another example of a group. The definition of a group is so important because it codifies the notion of symmetry. If we have a symmetric object, then we can consider the set of symmetry transformations. So for example, so if we have a ball, then we can consider transformations of the ball that preserves the overall shape. Or, so in this case, we have a ball with a specific pattern on it. So now we can consider transformations or motions of this ball that will preserve the pattern. And so the group in this instance will be the set of all symmetry transformations of a given symmetric object. So it turns out that such a set always carries the group structure. So there is an identity element. So this is a symmetry transformation which is lazy. So we have a symmetry transformation that does nothing to our object. And then we have operation of multiplication, which is a composition of symmetry transformations. So if we have two symmetries of an object, then their composition is again a symmetry of an object. So if we have this sphere, so then we can rotate the sphere around this axis and then rotate it under a different axis, and the composition of these two rotations again will be symmetry transformations of a sphere. And every symmetry transformation can be undone, so it has an inverse. And so it turns out that these three axioms of a group will hold for the set of symmetry transformations of any symmetric objects. And because the notion of symmetry is such an important notion in nature, so because of this, the group theory becomes a very rich and important theory in mathematics. Let us consider more examples of groups. So we claim that integers, so the set Z, with operation of addition instead of multiplication, forms a group. Now, so when we discuss groups, so what's important for us is not the notation for the operation of multiplication, but the properties. And we already saw that in the group of permutations, the multiplication is denoted not by a dot, but by a circle. So why not use other notations for the group operation here? So let us check the axioms if we use plus as our group operations. So the associative law will read as follows. So x plus y plus z is equal to x plus y plus z. And we certainly know that this law holds for addition of integers. Now, let us look at the axiom of identity. So how can we write down the axiom of identity if we use plus for our operation? So then this will be written as x plus identity, and identity plus x is equal to x. Now we have to decide what is the identity element in the set Z with respect to operation plus. And clearly, so from here we see that if we take plus as our operation, then we should take 0 as our identity. So 0 becomes the identity element. And indeed, we can check that x plus 0 is equal to 0 plus x is equal to x. Now we have to think about the inverses here. So what is the inverse operation if our multiplication operation is plus? So then here, so let us write down the axiom of the inverse. This axiom says that when we take the product of x with its inverse, then we get the identity element. So now, what should we take as an inverse to have the following? X plus something is equal to identity element, which in our case is 0. And so then we see that the inverse with respect to addition is the unary minus operation. So here, so the inverse in the context of integers with multiplication being replaced by a plus is the operation minus x. So we take the opposite element. And then the axiom of inverse will read in these new notations as x plus minus x is equal to minus x plus x and is equal to identity element, which is 0. And so what we see is that if we take the set z with binary operation of plus and distinguished element 0 and the operation unary operation minus, then in these new notations, all the axioms of the group will hold. And so this means that this will give us another example of a group. This opens the gates to more examples of groups. So now if we take real numbers with operation of plus, right? So the identity element being 0 and the operation minus x. And again, so this becomes a group with respect to addition. Now, if we have a field f, then each field actually gives rise to two groups. So one is the additive group of a field. So which is this field with operation of plus, the 0 element as the identity element, and the operation minus x as a replacement for the inverse. And we have the multiplicative group of a field. So here we take the f star. So this is the set of all non-zero elements of the field, and with operation of multiplication, and so with identity element being 1, and the inversion being x inverse. So now, if we take the set of non-zero elements, so these are non-zero elements, then we know that the set of non-zero elements is closed under multiplication, because the field has no divisors of 0. The product of two non-zero elements is non-zero. And so we see that all the axioms of a group will hold here. So this means that with each field, we associate two groups, the additive group and the multiplicative group. As special cases, we get the set of rational numbers with respect to addition and the set of non-zero rational numbers with respect to multiplication. We get more examples of groups if we consider remainders mod m. And so here we have the set Zm with respect to addition. So this will be a group with identity element being 0 and the operation minus x. But also we can take Zm star, so which is invertible remainders. with operation of multiplication, because the product of two invertible remainders is an invertible remainder. As the next example, we take V, a vector space, over a field F. And so if we take addition of vectors as our binary operation, then 0 vector as the identity element, and so the operation minus V as a replacement of inversion, then we see that the axioms of the vector space will incorporate the axioms of the group. Well, we know that we must have an associative law for addition of vectors. Then we should have the axiom of a 0 vector and the axiom for the opposite vectors. And so this means that this will become, again, a group. Every vector space may be viewed as an additive group. We can also see that we can generalize our example 3. And we can consider general linear group in the context of any field. So this will be GL and F. So these are invertible n by n matrices with entries in field F. And this will be a group with respect to operation of the product of matrices. So here the identity element is the identity matrix, and the inverse is matrix inversion. Let us mention the following definition. So a group G is called commutative or the synonym for this is abelian if for all x and y in G, x times y is equal to y times x. So this means that the multiplication is commutative. So what we see is that many examples on this list are commutative groups. So for example, this group R star is a commutative group. So when we multiply non-zero real numbers, x times y is equal to y times x. Or in the context of fields, both the additive and the multiplicative groups of the field are commutative. But also we saw that some examples of groups are non-commutative. So notably Sn is non-commutative. So we saw that the product of permutation is different if we take them in different order. So x times y is in general not equal to y times x. And another non-commutative group is GL and F. So we know that multiplication of matrices is also non-commutative in general. The term abelian is in honor of Norwegian mathematician Niels Abel, who was one of the pioneers of group theory. Let us return to the study of permutations. So suppose A1, A2, ... AK be a sequence of distinct elements in the set 1, 2, 3, n. So distinct means that they are pairwise unequal. And then so we define a cycle, and the notation is so we use single row notation for cycle A1, A2, ... AK is a permutation sigma in Sn defined as follows. Sigma applied to A1 produces A2, sigma applied to A2 has value A3, and so on. Sigma applied to AK minus 1 has value AK. Sigma applied to AK has the value A1. And for every element B, which belongs to set from 1 to n, but which does not belong to the set of A's, sigma of B is equal to B. So this means that a cycle permutation will permute elements of this cycle by shifting them, and the last one will go to A1, and all elements are not in the cycle will be preserved. So let's consider an example. So suppose we have the following cycle sigma. So 1, 6, 3, 2, right, is as an element of S6. So what is sigma in our two-row notations? So 1 will go to 6, 6 will go to 3, 3 will go to 2, and 2 will go back to 1. And all elements that are not part of this cycle, they are preserved. So this means that 4 goes to 4 and 5 goes to 5. And let us state a theorem about cycles. So any permutation sigma in Sn may be factored as a product of independent cycles. So which means that the sets that each cycle will permute do not overlap. Now let us consider the following example of a permutation in S12, in symmetric group of permutations of length 12. So let us try to factor it as a product of independent cycles. So how do we do this? Well, we start with 1. So we see 1 goes to 7. Then we trace it and we try to see where 7 will go. 7 will go to 8. Then 8 will go to 2. And 2 will go to 11. And 11 goes to 1, thus completing this cycle. But this cycle does not cover all the elements in this permutation. So then we should take something which is not here. So we take element 3. So 3 will go to 9. And 9 will go to 12. And 12 will go to 5. And 5 will go back to 3, thus completing this cycle. Now, did we cover everything? So no, we don't have a 4 here. So we have 4 that goes to 10, and 10 goes back to 4. So this completes this cycle. And the last element, which is not here, is the element 6, which forms a cycle of length 1 on its own. And so what we see is that really, so this permutation sigma can be thought of as a product of these 4 cycles. So we have a cycle of length 5, a cycle of length 4, a cycle of length 2, and a cycle of length 1. And so thus we have this very simple algorithm. How can we take any permutation and break it down as a product of cycles? And so the existence of such a simple algorithm makes this theorem rather obvious.